All right, so let's move with TCP if you don't have any questions. So TCP is a really big one, so that's the reason I need 2 lectures with this. So once again, TCP is reliable and efficient. We need to define what do we mean by efficient. It uses a byte stream, so I already explained a little. Byte stream is due to the fact that you have some very hard requirements on the size of the segments. Okay. We have multiple types of segments, so we will need to explain each of them. So this is quite important. In order to be reliable in the header, we put sequence numbers, and we use acknowledgements. Okay. We have a TCP connection, so we need to see how to set it up and how to tear it down. We have flow control to avoid the receiver from receiving too many bytes that cannot keep on with. We have urgent and push bytes as well, plus options. So you see, so there's a bunch of stuff that we need to study. Anyway, so what you send is not a message. So as I already said, when the application is writing a block of bytes in your buffers, that's not what you're going to send. Okay. So what you send, TCP just look at the bytes as a stream of bytes. There's no separation. You need to set up a connection, and so you need states. The states are included in the TCBs that you create when you have the connection. It is reliable thanks to the checksum. You can detect if you have corrupted data. You use sequence numbers to make sure that actually you didn't lose any data, but as well to reorder the data in case the segments are received out of order. And in order to make sure that actually you can repair the losses that you detected, you use acknowledgements plus retransmissions. So we'll see actually to retransmit, you also need some timers. When should I retransmit? We had the flow control. You try to avoid overflowing the receiver with too many bytes. And congestion control is to avoid congesting the routers. So the reliable service, so it's based on the connection. And the connection, as I said, and it's really important, is about creating states and maintaining those states. Including those states are the buffers, sequence numbers, the windows. So we're going to see that the flow control use what we call the window and timers. For the error detection, I use a checksum, okay, that include the pseudo header. For the loss detection, I use sequence numbers. And what we sequence is not the messages, but the bytes that you carry. So it means that if I have a TCP, the sequence number that I have in TCP is the number of the first byte. So it means that if here I have 10 bytes, and this is the following segment. So if I have 10 bytes, what is the new sequence number for this one? So it's SN plus 10, yes, because this is number SN, the last one is SN plus 9, since you have 10 bytes. So be careful with this. So when you do plus 10, is the following here. So yes, plus 10, because what your number is the bytes and not the segments. All right. So what else do we have? We have the recovery. So once you can detect loss, you need to make sure that actually you can retransmit the missing segment. So you do that by using positive acknowledgements plus timers. All right. So that was about being reliable. All right. We said it's reliable and efficient. Let's talk about efficient. So to be efficient, it all means that TCP will end up sending frames that are full. Okay, you never send small frames at the layer 2. So when you're going to create the segment, you're going to create it only if you have enough bytes that will match the MTU. And you remember the MTU is the size of the data inside the frame at the layer 2. So you remember here we have a frame with the header here. We have the MTU here. So it means that TCP at the layer 4 will take bytes such as is going to match this size. Okay? And so since we know that here we're going to have the header that is added by the layer 3 plus the header that have been added by TCP, you see that this data is equal to the MTU minus the size of the headers. This way, TCP will grab as many bytes as will match exactly the size of a frame. So you try to avoid sending half-full frames plus avoiding fragmentation. This is really important. The other thing that we do to be efficient, so this is one, the size of the segment. The second is you try to avoid losses, okay? So what do we mean by that? Is like sometimes the losses can be avoided. So we already explained that the losses may happen when you overwhelm routers or the receiver. So in order to avoid those losses, we have a feedback control where the receiver gonna tell the source that, oh, stop, I cannot receive any more segments. So the receiver gonna control how many bytes the sender can send, such as you never overwhelm the buffers of the receiver. And for the congestion control, we do the same. The routers have a way of sending some kind of feedback to the sender, right? So what we mean by that, you avoid the losses by controlling the sending rate of the senders, okay? And we're gonna see that in user window. The other thing that make it efficient is TCP is fair. We already talked about it. If you have two TCP connections sharing the same path, both TCP connections gonna use exactly half of the bandwidth. So you share the bandwidth in a fair way between multiple TCP connections, okay? You remember that when you have a pipe here and you have R, each TCP connection gonna receive the same ratio of the bandwidth because TCP is fair. You remember in HTTP when we talked about it. So those three elements here guarantee that TCP is efficient. The MSS is the maximal segment size, but you have to be careful. The MSS is only the data. And the MSS will be based on the MTU, which is here. And you basically gonna create a segment with as many data as needed, such as you can match properly the size of the data in the frame. So once again, in Ethernet, we know that this is 1500. So if here we have 20, it means that the MSS should be 1460, right? That's it, very simple. So not a big deal about it, but what it means that TCP gonna be stopped until it have enough bytes, MSS bytes to be sent. So you're gonna wait until either you have enough bytes or you have a specific timer in TCP that's gonna expire and tell TCP that you waited too long. So now you should send whatever bytes you have, even if you don't have enough of them. So you may have a timer, but you also have what we call the push. Is a function where the application can say to TCP, don't wait any longer because I don't have anything more to write. So the application, after writing the bytes, can try to push the bytes and to force TCP to create a segment, even if the segment is small. So two ways of actually sending small segments, either expiration of a TCP timer or a push coming from the application. Let's look at the header now, because when we study protocols, everything is about a header. And as you may see here, what is the size of a TCP header without the options? 5 lines, 4 bytes per lines, so we have 20 bytes, right? So here it is. So 20 bytes. 5 lines, 4 bytes for each line. Plus some options here. Okay? But the fixed size is always 20. So what do we have here? So we have a bunch of information. So let's go over the reason of those. Port numbers, why? Because we need to do some multiplexing. You remember? We may mix multiple TCP connections coming from the same end host. So to make sure that to know which application is sending or receiving, we use port numbers. Good. What did we say regarding the sequence numbers? Sequence numbers is because we need to be able to ID which bytes are missing. So if you lose a segment, you know that there's a missing segment thanks to the sequence numbers. All right, so actually we use the sequence numbers, the acknowledgement numbers, plus the checksum. So those are used in order to ensure that this is reliable. The checksum is for the corrupted bits. The sequence number is for the missing segments or the segments that are received out of order. Make sense? So you see why do we need those fields? Okay. What else do we have? We have the window. So the window is what we use for the flow control. So to make it easy, what it means that whenever the receiver is sending us a feedback, a segment, it will tell us what is the size of the available buffers that it has. And so the sender should never send more bytes than those specified in the window. So the window is the way of telling how many bytes is the receiver ready to receive. And then those ones here, this is the connection management. So we also use the sequence number. I will explain about this. So this is when you need to either set up or tear down a connection. So now you have the complete picture of the reason of each of the fields. All right? So that's the reason we end up with 20 bytes. So what is interesting to see here is the flags. Those are the flags. And those flags can be set such as it can give to the segment a different meaning. So what do I mean by that? I mean that you remember what we said that I send a seen segment. The seen segment is the fact that that specific flag here, which is located here, is equal to 1. And this is the very first segment that you should send. So that segment, which actually doesn't have any data, is a seen because you put that flag. But once you send your seen and now you have data to send, you don't use the seen anymore. The seen is only for the segment that you send to set up the connection. Okay? So that's the reason you have flags here to give a different meaning to each segment. You remember I talked about the push. The push is whenever the application indicates that those bytes should be sent right away. So when you push the data, the receiver is going to know that, oh, I should read as fast as possible the data that the application have pushed at the sender. So that's the reason you need the push segments. All right? So the port numbers. So once again, when you send the source, so the source and the destination port number, okay, self-contained here. If it's a client sending, the client always use a random value if it's not a service protocol such as DHCP. But when you use any other kind of application, the value that you use as a client is a random value. And usually it should be always larger than 1023 because it's not a reserved one. And usually when you design an application, you let the operating system choose that value. On the server side, if you send your TCP, so it should be a seen properly, you use the well-known port numbers that ID the service. All right. So TCP is a little bit weird. So you need to understand that actually TCP was improved over the years. And so when they started, they didn't really expect to need different type of fields, different type of segments. So in order to specialize a segment, what they did, they introduced the flags. So the flags is the way to indicate that this is a special segment. And it is so crazy is the fact that the data segment, the basic segment, which is just to carry data, doesn't have a flag. Okay, so the default type is data. We don't have a flag for this, but we have flags whenever we need something specific. So we already said that we have the seen and the fin for the connection, setup and tear down. We have the acknowledgement for make it reliable. We have the push and the urge, and I'm going to try to explain you later the reason we need those, but this is something that can be set with data. So acknowledgements as well, we can actually biggie pack an acknowledgement with data as well. So acknowledgement doesn't mean that it's empty. The only case where actually the segment going to be empty is whenever I have the seen, the fin, and the RST. In that case, there's no data. Okay, so those are the specific cases where I cannot have any data. which makes sense because I cannot send data before the connection is set up. Makes sense. All right, so let's look about those type of fields. So the first one is the SYN. So the SYN, you may remember, this is what we use. So it's a three-way handshake because we have 3 messages at least. And it is only after those 3 segments sent and received that the connection is established. So you can see that for the client, the connection is established when you acknowledge a SYN. And once you receive this one, is acknowledged on the server. So we do that in order to avoid, we want things to be set up initially. So the SYN stands for synchronization. Why? Because we need to synchronize the sequence numbers. We already said that when I send the data, we don't start numbering the data, the bytes inside the segments with the value that start at 0. We take a random value. Okay, so when I have X here and Y, those are the random values that have been used. So it means that in the data, the SN, the sequence number of the first data that I'm going to send, is equal to X plus 1. We already explained the reason for X plus 1. And the same goes on the other side. When I'm sending the data here, the first SN will be Y plus 1, giving that the initial sequence number was Y in that case. All right, so that's the way it is. So we can see that when we send an acknowledgement, we're going to increment the sequence number if it's a SYN. And if it's a data, you remember that we are advertising the next expected sequence number following the last byte that we receive in sequence. I'm going to go back to this. So what do we need a random value? So I'm just trying to show you here why we don't start numbering from 1 or 0. So I could just give you here an example where actually we make a fake assumption here, and we consider that we start numbering with the value 1. You can see it here. So on both sides, the ISN here is equal to 1. The ISN on this side is equal to 1. So what do we try to avoid it? Well, the thing goes as follows. So let's say I'm starting, so I'm not sure if the values are good. Oh, no, I'm sorry. I did, that's the flags here. I did a different, so those are the flags, flags. So we can see that in this case, the flag SYN is set, no acknowledgement, and the ISN is 0. You can see it here. The same goes here. So I'm sorry I took this example. So which means that the first data that I'm going to send have a number 1. Okay, the sequence number of the first data that I'm sending is 1. And let's say that for some reason, that very first segment of data that I'm sending in that connection is delayed in the network. And at the same time, this connection, for some reason, is reset. There's like a crash, one of the 2 endpoints crash, and they restart exactly the same connection. And look what can happen here. So I'm going to try to do exactly the same connection again. And I'm going to start sending, after the connection is set up, my own segment. And you can see that this segment here that I'm sending, and this one that was a connection from a previous attempt, you can see that what's going to happen, the legit segment is going to be discarded because we're going to have the same number twice. And so TCP will have no way to flag the fact that the first segment actually was belonging to a previous attempt. So in order to avoid this kind of scenario, that's the reason we put the random value here, let's say X. If it's random, it means that the second time I'm going to have X prime. And since X prime is different from the X that we used to have here, we can discard the segment belonging to a previous connection using exactly the same parameters, meaning the IP addresses and the port number, okay? So this is the main explanation for having random sequence numbers. Do you understand the reason we use it? So that's the way it is. I mean, because I know to some of you guys, you may be like, why should it be random? Well, that's the reason. So then we saw the SYN. The same way we have the 3-way handshake for setting up a connection. We have a 4-way handshake to close the connection. And you may remember that when you tear down the TCP connection, mean you remove the TCBs, okay? So at some point, we establish the connection. We have states in memory of both endpoints. When you send the FIN, means at some point you need to tear it down. It means that you need to remove any state that you maintain for that connection. So we may see that we have 4 messages. So on this side, we have the 2 messages, 2 others. So that's the reason it's a 4-way handshake. Okay. And what you need to understand, the meaning here is when the client sends the FIN, it only tells that I won't need to send any other data in the future. But it doesn't mean that he's not ready to receive data from the other side. So you just close your endpoint of the connection, meaning that you don't have any more data, which means that in our case here, we can still receive data until I receive the FIN from the other endpoint. Okay? And in that case, this is, at this point, you can say that the connection has been closed on both endpoints. All right, so 4 messages. The messages that are coming from the client only means that I don't have any more data to send, but I can still receive, okay? So if we look at what we have, so once again, the connection have a 3-way handshake in order to establish the connection. I can also, in the ACK that you have here, I can basically piggyback the request, which is like a HTTP request with the acknowledgement. So this is a 3-way handshake. Then you receive the response. And in this case, for instance, I wait later in order to send the FIN. As I said, the FIN could have been sent even just after the request. Okay, so there's no really, it depends on the behavior of the application. And so this is when you actually send the FIN that the TCB is terminated. So here you create the TCBs, and here you tear them down. So you may see that actually you don't tear it down immediately at this point. You wait a little bit, and the reason for this is pretty obvious. So I'm going to show you on the quick one. So let's say you send a FIN, and you have the acknowledgement, FIN ACK. Okay? And then you have the FIN in that case. This guy will expect the acknowledgement. Let's say this acknowledgement is lost. What's going to happen on the server side? If the server doesn't receive this acknowledgement, what's going to happen? So if it's my client and the server, what the server is going to do, since he's expecting the acknowledgement, he's going to send again the FIN. So we will see that we have a timer. And I'm going to send the FIN again. So you see, so if actually I terminate my TCB at this point, if I terminate it here, and I'm receiving the FIN again, there's a problem because I don't have any trace of the connection that I used to have. So that's the reason after sending the acknowledgement, I need to wait at least for a given period until I'm sure that the FIN won't be retransmitted. So if we go back to what I was saying just before, so it means that when I have my FIN, and I have the acknowledgement, and then the FIN from the other guy and the acknowledgement. So the server will terminate the TCB here. In the case of the client, he will need to wait for that duration before he can terminate the TCB. So the TCB is over here. So you need to wait for a round trip before you can terminate the TCB on your side, which makes sense. Okay, so that was about the connection. Let me remove this. Okay, so now here I give you the whole sequence numbers, and we already run this example on Monday, right? Last Monday. So you may see that what do we have? So here we have the ISN. The acknowledgement is a +1. The acknowledgement is a +1. You may see. The acknowledgement, as we see, we need the SN, the sequence number, but actually we don't consume that number. So it means that when I send the data, I can reuse the X+1 since it haven't been used in the acknowledgement, since the acknowledgement was empty, all right? And when I have the FIN goes the same. You see that the number that I have here in the FIN, okay, is acknowledged in which case here. So you have +1. And the FIN that I'm using here is acknowledged here. Acknowledgement have 2 different kind of behavior, and you need to be always careful with this. So either you acknowledge a SYN or a FIN, so you just do a +1 to the previous sequence number. If it's data, you need to acknowledge the size of the data that have been received in a segment. So you don't do +1, you do +1, giving the last byte that have been carried in the segment, the data segment that you acknowledge. Okay. So when you have the data segment, as I said before, there's no flag indicating that this is data. Nothing going to tell you that this is a data, but you may have other bits, the other flags that have been set up. You can have the acknowledgement if you piggyback the data with an acknowledgement. You may have a push or a URG. So we're going to see them later. So the sequence number is, as I said, those two fields. So this is the SN, the acknowledgement number. So those are pretty important. So the sequence number have a different meaning depending on the flags. So either is a SYN or a FIN or data. So you need to be very careful. Is there data or not? Because the behavior of the sequence numbers won't be the same. And the same goes with the acknowledgement. So when you acknowledge the data, you always need to refer to the last byte that you are receiving, +1, okay? If it's a SYN or a FIN, you're gonna acknowledge just by taking the sequence number of the SYN or the FIN and do +1. So here I'm detailing all of this, so let's go over. So this is a 32-bit, okay? The sequence number in a SYN is a random value that it is actually randomly selected. It's never started by 0 or 1. It's already a random value. When you want to acknowledge a SYN, you're going to take the value in the sequence number and you're going to increment it by 1. If it's a data segment, what you're going to do, you're going to increment by 1, but by considering the last byte of the data. So this is really important. And when you have a FIN, in that case, you take the sequence number of the FIN and you do +1. That's it. What else? So when you have TCP, a TCP segment can also be an acknowledge, and you need to have the flag in that case. So it means that a segment doesn't have to be a flag. It needs to be specified using the flag. So sometimes you have nothing to acknowledge, so you won't have the flag. And the acknowledgement, as we said, is calculated depending on the sequence number of the segment that you acknowledge. So if the segment that you acknowledge is a SYN, a FIN, or RST, you take the SYN and you do +1. If it's actually a data, you're going to take the number of the last byte of the data that is carried and you do +1. So you need to be careful with this. So the SYN, so we said that the acknowledgement segment, okay, may be piggybacked with other flags. So those are the typical combination. And it can be also piggybacked with data. The sequence number of actually an acknowledgement that is empty without any data is actually not relevant. Okay, so you remember that what we're going to do, we're going to reuse the number, which is the one expected by the receiver. Okay, so we're done with the port numbers. We're done with the sequence and acknowledgement number. So the other field that we have, and as you may see, you have to be super careful. This is a 4-bit long field, is what we call the THL for transport header length. So it means that in the TCP header, since we may have options and this size is variable, it means that since we cannot know what is the actual size of the header, we need to specify how long is a header. So in order to do that, we have THL, and it is 4. And actually 4, what does it mean? You see that without options, we already have 20 bytes. So how can I put this value here? Actually, what we have here is the number of 4 byte words in the header. So which means that if I have the maximal value on 4 bits, 15. So to know how many bytes, we said that those are the number of 4 byte words. So times 4 equal 60. Very good answer. So it means that I have 20 here for the standard header without option. 20 is here. So since the maximal we can have is 60, how many max byte for the option? How many options can I have in total? 40. Very good answer. The thing also that should be a little weird to you guys is the fact that, oh, but the header need to be a multiple of 4. Yes, there's an alignment requirement. Any header, whatever is the size of the option, need to be aligned with 4-byte ports. So which means that if I don't have enough options to fill the last line, I'm going to add padding with zeros, for instance. I'm going to put as many zeros to make sure that the size of the header is a multiple of 4 bytes. So we used to have 32-bit processor CPUs, right? So it means that the registered were very well designed. You load 4 bytes and you process them. So in order to speed up the processing of the header, you just load as many words. The size of the words should be aligned with the register. So 4 bytes. Obviously, IPv4 is also a 4-byte alignment. Guess what? Since we have IPv6 now, and IPv6 is much more recent, what is the alignment for IPv6? Because nowadays we don't have any more 32-bit chipset, right? So what is the alignment nowadays that should be the most efficient? Which is 64 bits, right? Yeah, 64 bits, which is 8 bytes, right? So in IPv6, the alignment moves from 32 bits or 4 bytes to 8 bytes, which is 64 bits. All right, good. Anyway, let's talk about the window now. So the window, as we said, this is what we use in order to do flow control. And the flow control is in order to avoid the sender from overwhelming the buffers of a receiver. Because the receiver, as you remember, you put the bytes in the buffer and you wait for the application to go read the bytes. So it means that the buffer is going to fill up. If the application is very busy and cannot read the bits, the bytes that you have inside the buffer going to fill up, and for any bytes in excess, they're going to be dropped. So you try to avoid those losses. To avoid these losses, it means that anytime you receive a feedback from the receiver, you're going to indicate a window, okay? And the value of the window is equal to available buffers that you have at the receiver. So this way, you may regulate how many bytes the sender is authorized to send. All right, so this is how you do the flow control. So this is how it works here. So what do we have? So let's say this is the sender here, all right? And so the sender have bytes. So those are the bytes that have been written by the application. And so it means that at some point, you may send the bytes. So I have different colors here to show you that those have been sent already. And for those, you have received an acknowledgement. So those basically don't need to be retransmitted later. So you may drop them. Later, what do you have? You have the window, which is actually how many bytes the receiver have allowed you to send, giving the size of the window. So this is the size, how many bytes you can send. And out of those bytes, you have those that you already sent, because you cannot empty the window right away, right? You send the bytes little by little, by segments. So at some point, some of them have been sent, okay? And you should be able to see that, byte already sent, in flight, en route in the network. And then you have those you may send in the future without waiting for the acknowledgement. And on top of this, after the window, what do we have? We have those that have been written by the application, but are not yet authorized to send them because they're outside the window. So what's going to happen now? If I look at this picture here, all right? So what makes move this boundary here? What will make it move on the right? You see, it cannot go on the left. It needs to go on the right. What make it move to the right? Can anybody tell me? What is the event that's going to, an acknowledgement. And obviously, it needs to be an acknowledgement for one of those bytes. Okay, so I acknowledge new bytes. It's going to make it move. Okay, good. What's going to make it increase or change the size? So you see, that's going to slide the window. That's going to push it. But as well, when I receive the acknowledgement, there's a new value for the window. So the new value of the window will give me this one here. So this will depend on the window that I receive. Is that right? This one move as I'm sending the segments. And this one here move as the application going to write new bytes. So you see how this window is moving? And depending on the size, I can control how many bytes I can send at some point in the network. And this is all based on the acknowledgements that I'm receiving and the value of the window. So the window is moving because I'm receiving a new acknowledgement with a new value for the window. So those are going to make move the two pointers that you can see. The one in the middle is the fact that I'm sending the bytes inside the window. And this one is because the application is writing. And in overall, the purpose is to move the pointers to the right, okay, by controlling how many bytes I can send. So please put a note somewhere. If you go for a master degree or whatever, you're going to see that this is not the only window that we're using. We have a second window, which we call the congestion window, okay, congestion control window. And the size of that second window is designed such as we want to avoid overwhelming the routers in the network, okay? And what we do, we take the minimal size, we compare the two windows, and we take the minimal size. So maybe the flow control could be smaller, maybe the congestion control going to be smaller, and that is the exact size of bytes that I can send, okay? So keep in mind that we have two windows. In this course, we're only going to study the flow control window. All right, good. So what time is it? Okay, we still have like a lot of time. That's good. So we already talked about the checksum. So the checksum is pretty much similar to UDP. And what we have here, so again, we have some values that are coming from the IP header. This is a pseudo header. We use it on top of TCP in order to do what? To sum. You remember we do the half, we do the complement, and we put the value in the checksum. All right, so this is just a summation, okay? Not a big deal here. So the push flag is something that's gonna act on the sender side and the receiver side. So what happened when we use the push? So you may remember that TCP won't send the bytes if it doesn't have enough bytes for the MTU of the layer 2. You remember? So we want to be able to create a segment that will match perfectly the size of the frames. You remember that. So, but sometimes the application may judge that, oh, you know something, I just finished writing. I know that I don't have any more data to be sent. So if you're stuck because you're waiting for more bytes, no need to wait. So that's the reason you're going to put at the application layer a push indicating to TCP that no more bytes, send right away, even though the segment is super small. All right. And so this is on the sender side. So please don't wait for the timer, okay? Because we don't have more data to be written. And on the receiver side, it's gonna you're gonna push the application receiver to come and read as soon as possible the bytes. So this is just a notification. The application doesn't have to really come and read it, but it's just an indication. So if the application have been designed such as it can take into account that push notified by TCP, it may go read pretty fast the bytes that are already available. So this is good for, let's say, some interactive applications that need to receive as soon as possible the bytes and so on. So the push may be useful in order to make things go a little faster, okay? But this is not a requirement. So it doesn't have to, it should do it, okay? And then we have the URG. So the URG is pretty interesting. What it means, and I have a slide regarding this, it means that, let's say, I'm going to show you later. Okay, you may read it, but let me show you later what I mean. So let's start with the push. So as I said, even though here you see that you have bytes that are not enough in order to fill the MSS, which is actually the size that I should have inside the frame, you may, without waiting for the timer, send right away the segment. And the push also will be a notification to the application receiver who will read as soon as possible the bytes that have been received, okay? So this is how it works. So you may go read the RFC, which is the standard for TCP. It's really unclear how to implement this, but you can see that in some case, if you do some Wireshark, you can really see that indication. It's really used by some applications, okay? So for the urgent, what do we mean by urgent? So let's say you have a byte stream, okay? You have a stream of bytes that need to be sent. So what do we have here? We have the bytes that already been sent, but haven't been acknowledged yet. You have some bytes that are waiting to be sent, that already been written by the application. And at some point, the application realized that, oh my God, I need to send some bytes more urgently. They need to be sent before the blue ones, for instance, or the green ones, okay? So what's gonna happen here? You can see that inside the segment, I'm gonna use those data that have been flagged as urgent by the application, and they're gonna be sent in priority compared to the blue ones, which will be weighted. Normally what we're doing is a FIFO, first in, first out. Thanks to the URG, what you may do is to overtake some bytes already in the buffer, such as you can send them before. And so that's the reason here you see that the red ones come first. And if there are too many of them, they may fill the whole segment, okay? So you may combine them. So since you don't really send an urgent segment, but some bytes may be urgent, we have in the header the urgent pointer. And the pointer gonna indicate how many bytes inside the segment or even in the following segments have been flagged as urgent, okay? So the same way you send them first, you need to read them first. So even if you already have some bytes waiting to be read by the application, they're gonna come first. So then we have the options, and you remember that we may have options for values that are greater than 5, okay? Because 5 times 4 is 20. So if we have options, so, and you see that I didn't say, but actually it should be smaller than 15 or equal to 15. All right, so when it's 5, no options, it can go up to 15 to indicate that there are options. So the options actually, they use a specific format in order to indicate the options. So let's see about the options. So as you may see from this table, there's a huge number of options, right? And most of them are not used. So don't worry about it, okay? So the ones that are really used are the one on the top, and that's the one we're gonna talk about, right? So first of all, we have 2 specific options. The first one is called the EOL for end of option, and the other one is the no operation. And those options are very specific because they are only 1 byte long. 1 byte long. So you may have multiple of them, but one option is 1 byte. So what do we need then? This one is used in order to do the padding. Remember we said that if you don't have enough options to match the requirement of the 4 byte alignment, you may use padding. This one I'm going to show you in the example later. This is something that you're going to place between 2 options to space them out enough, such as each option start on the clean line. So instead of having an option that is half-half on 2 lines, which is really hard to handle, we may push one option as far as we can to make it start on a new line, okay? So that's the reason. This is a kind of a special padding that you put in the middle of the message. At the end, it should always be the zeros, okay? I'm going to show you an example in a minute. Any other options will always be specified as a first byte with the kind, so it's a type, then the total length of the option, and if any, the data that comes with the option. So let's take a few examples for those ones. We have what we call the maximal segment size. So what do we mean by that? It means that when I send this option to somebody, so this is the option MSS, I expect them to never send me segments larger than the value that I provided. So this is not regarding my segments. This is, I indicate to the sender that I'm not willing to receive segments larger than those ones. So in order to understand this, it means that, let's say, if you are a receiver with a very small buffer, okay, and the server, whoever is sending data, is sending you like huge chunks of segments, it may overwhelm you by sending a couple of segments. So in order to control a little bit more how many segments you can receive, you can force them to send you small segments that are much more consistent with the size of your buffer. So that's the reason you may want to indicate the maximal size of the segments. All right. So here, type 2, the length is 4. So it means that here we have 2, and this is where you're going to have the size of the segment that you want. All right. Good. Then we have the Windows scale. So what does it mean? It means that you remember the window is 16 byte long. So it means that this is 64K. Well, nowadays, most of the buffers that we have are not so limited. 64Ks, I mean, come on. We all have computers with like gigabytes, right? So that's the reason, since this length is outdated, we added an option that is a kind of a shift. We're going to indicate how many zeros you put at the end, which amount to multiply the value by 2 as many times as you have the shift here. So it's to increase the value. So when you have this value, you may take the window in the main field, the main header, and multiply by 2 as many shifts that you have. So the total size is 3. No problem, that's good. And then we have the timestamp. So the timestamp is really important. So this is a very long option, as you may see, 10 bytes. Type is 8. The total length is 10, A. I put the value in hex. And something, guys, that you should always remember, all right? The values in hex, if it's 1 byte, you should always provide me with a 0. If you don't put the 0, it means that you don't understand the length of the field. And I don't know if you're wrong. So even if there's a 0 in hex, never drop the 0. In networking, it's really important to keep the length of the field. Okay, so if it's a 1 byte and the first is 0, you still need to tell me the 0. Okay, so don't skip that one. And then you have two main values. You have the timestamp and the type echo reply. And as you may see, what is happening here. So maybe I can do you something that is a little bit more schematic in order to understand. So you may remember that whenever you send some data and you expect an acknowledgement, and if you don't receive the acknowledgement, at some point you will need to retransmit the data. You remember that? Pretty simple. But this requires a timer. But the big question is, how do you calculate a timer? Because it depends on where is the sender or the receiver, right? It depends on many factors. So you cannot really use the default value. So what we do in order to avoid this is we take this option. And so what is happening? Whenever I send a segment, let's say this is my first segment. So I'm sending this at time t. So this is my clock. So what's going to happen? I'm going to send in the timestamp option t0. This one is received by t prime. So I'm going to send in my option t prime and the t. So it means that when I receive this segment, you know, I'm going to realize that I'm receiving this at t prime. So based on the t, that t, I'm going to do t prime minus t. That's going to give me that value. So basically, I don't need to keep this in my memory. I don't need to keep a state. Why? Because that will be carried back, and I can calculate the difference. The same going to happen here. So in the timestamp, I'm going to put, what are the values I'm going to put? T prime. So which means that when I receive this here, so this is going to be a t third, whatever. And to do the calculation, I'm going to do t third minus t prime. And I'm going to have this. So you see, so by doing this, I can do the calculation of the round trip on both sides. And I don't need any specific state. So this, I don't need to keep a state because I'm going to echo that value in the message. So this is very standard. I receive the value, do the difference. Here it is. I have the timer. Oh, so that's how this option is working. Okay. Oops, sorry. So this is what we have here. So here I gave you some values, but this is the same with t and t prime. So we will see actually how we use that measurement in order to do an average and use it for the timer. All right. Okay, so let's take a quick example. So this is my TCP segment. Okay. So once again, port numbers, here they are. Source, destination, port number. Is that okay? Yes. You remember that next coming is the sequence number. Here it is, sequence number, 4 bytes. Then we have the acknowledgement number. Oh my God, all zeros. So who can tell me if they're all zeros, what is the type of the segment? If there's all zeros, one of the very few cases where we have all zeros is a SYN. So let's keep it on in somewhere and we'll see that later. Coming next, if you go to the main TCP, we have THL. Oh my God, A. What is the size of the THL, please? If it's A, what is the total size of the header? 10, 10 times 4. So it's 40. So it means that I have 20 for the options. Yes, we have. And so then we have the flags. You remember the second one from the right is the SYN. Yeah, so we're good, right? It's standard with what we have. Then what we have else? We have the window. So the window is here. Okay, window. Then we have the checksum. Here it is, checksum, and the URG. So you see, so we have 0 because the flag, the URG flag is not set. So it's normal to have a 0 for the URG. All right, and then we're done with the main window. Then what we have the options let's go with the options. So the first option, 02, 02. You remember that the 02 is the MSS, 4 bytes. The value is on 2 bytes. 05 goes 15, 14, 40. That's the value of the MSS that I'm expecting. Then we have, oops, the time scale, the window scale. So no shift. So the value is okay as it is. So we don't need to shift the value. And then we have the timestamp. And obviously, you see that the second value is all zeros because it's a SYN. I haven't received yet anything from the receiver. If that makes sense. And you can see that here, I have this, this, and this. And you see that we use the knob to push the option, such as here, the 2 fields of this header, of this option are on a separate line. And these ones start on the clean line. So we just pushed it. That's it. Okay? So I give you just an example to see that what we've seen, this is what you get here. Okay, so going back to a few of the properties. So once again, you may remember that the MSS depends on the MTU. We already said about this. The other thing that we need to see here is the fact that the receiver is totally dumb. What do we mean by that? It means that the receiver keep acknowledging the data. So in case the receiver doesn't have any data, the only thing that is expected from the receiver is to acknowledge. But it's not the receiver who's going to detect any loss. The only thing is like I keep acknowledging the last number that I received. Okay? And actually the acknowledgement, there are multiple types of them. There's a delayed one, cumulative, and immediate one. So let's see when do we use them. So first case, so we have a segment that arrived in order at the expected number. So we don't send right away the acknowledgement. We wait for 500 milliseconds. Why do we do that? We do that such as we may expect a second segment from coming, and instead of sending 2 acknowledgements, we're going to send only 1. So that's the reason we call it a cumulative acknowledgement. All right. So let's say we have this example here. So I receive the acknowledgement with value A. So I'm receiving data with the sequence number equal to A. So I'm going to wait a little bit, and then I'm going to send the acknowledgement. Okay. So the maximum I wait is 500 milliseconds. Then we have another case where you receive a data which is out of order. Okay? So in that case, you shouldn't wait. You should send right away the acknowledgement. And it's going to be a duplicated one, and I'm going to show you that on an example. And then whenever we fill the gap, okay, so you're going to send immediately one. So duplicate the cumulative one, right? And the immediate for 2 cases, either there's a gap, right? Or it's because something is wrong, okay? So either you fill it or you have a gap, you need to be immediate. Anyway, so those are the rules. So let's take a few examples with retransmission using a timer. So what do we have? The last, yes, is the last. No, it's not the duplicate. No, the last one is the it's immediate one. You remember the last one. This one is an immediate one. All right, and is whenever you fill the gap that was left previously. Okay, so what do we have here? So let's see. So here you have a loss. Okay, so in that case, you see that you have what? You have a gap. So you're still going to acknowledge the one that you were expecting. All right. So, of course, the one that you were expecting is finally retransmitted. And so you're going to send 120. Why? Because you fill the gap. Okay. So it means that this one actually was in the buffer. So you keep in memory those who actually are still received okay, but after a gap. What do we have here? We have another case, and this is an interesting one. You may see that, let's say, this one is lost. So it means that for any of the new segments that you receive, you're going to receive duplicates. And so what is TCP telling you? It tells you that if you receive 3 acknowledgements duplicated before expiration of the timeout, before the timeout expires, you should understand that it means that 92 was lost. So you should retransmit it. So how many ways of detecting a loss in TCP? 2. Either timer expiration or 3 duplicated acts. So what we have here, we have the loss of the acknowledgement. So here, instead of losing the data, I'm losing the acknowledgement, but the action is going to be the same, right? So you may see, so that was a cumulative one, cumul. And so I'm not receiving it. So I have 2 timers. And for each segment, I'm going to retransmit it whenever the timer expires. This one here, what is this case? You see the timeout was too short. So it expired before receiving the acknowledgement. So in that case, I'm going to retransmit the sequence, this one, because the timer, the value was not consistent. Okay, so few cases where you can see that you can have, but it works at the end, right? It may be not efficient, but it works. So coming back to the timer, and that's really important that we see that, let's see the calculation and how do we calculate the timer. So the timer is really important for efficiency. Why? Because if it's too short, you're going to retransmit for no reason. So you're going to waste the bandwidth because you retransmit something that actually have been received. So you didn't give enough time for the acknowledgement to arrive, or it may be too long. In that case, you wait you introduce a long latency before you can repair a loss. So we need to find a way to do the estimation. And you remember, we have the timestamp option. And so what's going to happen? Anytime you have like a data segment plus the acknowledgement, that gives you a measurement of a sample for the round trip. But this sample is not good enough. Why? Because sometimes the sample could be very small, and sometimes it could be very big for some reason, right? So in order to smooth the value of the samples, we do an average. And you see that this is like a smooth average where we use actually 2 parameters, A and A minus 1. So here, this is the running average, the current value. And on top of this, we're going to add the last sample, all right? And usually the value for A is the standard value that is the recommended one. You can change it if you don't like it on your TCP, stack. But usually this is the value that is used. And based on the SRT that I have now, we take a value that is totally, how to say, conservative, meaning that even if this value is the average, we take twice this value. So this is how we do the calculation. So it means that actually the value of the retransmission timer evolves over time. It's never the same. And of course, by default, for the scene, okay, if we don't receive the CNAC, the retransmission in that case should be 1 second. So this is a new recommendation. Before it used to be between 3 and 6, which was very long. And still, 1 second is huge. It's huge. Okay? So here you're going to have a scene. Anyway, so the conclusion, because it's almost the time, my time is up, and I don't want to delay you any longer. So as we see, so we have 2 transport protocols, TCP, UDP. They share 2 functions, multiplexing based on the port numbers, and error detection thanks to the checksum, plus with a pseudo header and so on. In both cases, you protect the headers plus the data. In TCP, we have on top of this some specific services. So once again, we use a connection, TCBs, SYN and FIN, and so on. So the connection is related to the fact that we use states, okay? And this is the SYN, FIN, and RST. That's what we mean by the connection. We do loss and error recovery by adding a sequence number, by doing the estimation on the round trip, such as you can have a retransmission timer, okay, such as when it time out, you retransmit for any loss or even error. So what I mean by that is like whenever either you receive the data or you don't receive it, if here the checksum is wrong, you won't send an acknowledgement. So basically, in order to be able to repair error, the receiver is going to be quiet whenever the checksum doesn't check out, and he realize that this segment is corrupted, no acknowledgement. So in order to repair either a loss or a corrupted segment, you're going to use the same system with the acknowledgement. All right. Then we also have the flow control that uses a sliding window based on the announcement coming from the receiver in order to avoid overwhelming him with too many bytes. And on top of this, a congestion control. We won't talk about it this year, but if you want to go study about this, you can read in the textbook. It's pretty clear. I can point you to some pointers if you want to read about it.